Hello everyone and welcome to the first lecture of Materials and Manufacturing 2. We have already completed Materials and Manufacturing 1 when the focus was placed on the material side of the unit, making us familiar with crystalline structures of different materials and associated properties. And this unit focuses on manufacturing side of the unit will make us familiar with traditional manufacturing processes that are used in order to alter the shape and geometry of engineering materials in order to make useful products from the raw materials. The title of today's lecture is Introduction to Materials and Manufacturing, and the topics that will be covered in today's lecture are listed here. That is to provide a definition on the word manufacturing, what is meant by manufacturing and what is its modern definition. We will have a review of engineering materials. Those include metallic materials, ceramics, polymers, and also we will discuss briefly the composite materials. And then we will review some traditional manufacturing processes, and some of these processes that will be reviewed in today's lecture will be later discussed in coming lectures. And in the end, we will briefly discuss the structure of different production systems that are used in order to produce different products. Well, as we can see here in this slide, there are some 6 different products that are shown in the images. These are different types of products that we use in our everyday life. Starting from the top, we have got a simple part that is made of a single part. So there is a product and it is made of a single part only. However, in the other ones, there are more than a single part that are assembled together in order to produce the product. For example, in the case of the ballpoint pen shown here, there are some 10 parts that are individually produced and manufactured, and eventually they are assembled together in order to make this pen. Well, as we move from the top of the slide going to the bottom, the number of parts that are used in order to make the product will increase. For example, in the case of the toaster, how many parts are there in the toaster? Some 50 parts are individually manufactured and assembled together in order to make a toaster. Going down to the lawnmower, there are some 300, yes, that's correct, 300 parts individually manufactured and assembled together in order to make a lawnmower. Let's go further down to the car. That's the vehicle that we make use of it on a daily basis in order to get to work, to get back home, and to go to many places. That's a very useful product. And there is a lot of technology behind manufacturing of each of the individual products that are used in a car. How many parts are there in a typical car? Thousands, that's correct. There are some 10,000 parts in a typical car that are individually designed, manufactured, and assembled together in order to make a car. And going to the bottom of this slide, we can see the big jumbo, that one. Well, how many parts are there in a big jumbo? Yeah, that is correct, millions. There are some 6 million parts that are individually designed, manufactured and assembled together in order to manufacture a big jumbo that can carry hundreds of people or passengers in a flight. Well, so as we can see, all objects have been transformed from various raw materials into individual parts, and then these are assembled into different products. Regardless of how many parts are in each product and how big or how small the given product is, they all have something in common. What is it? They are all manufactured. Now the question that is to be asked is that, is it possible to live without manufacturing? Yes or no? Well, some people may say yes, but majority of people would say no. And also, my answer to this question is a big no. Why is this? Even if we don't want to make use of manufactured products and live like the early man, would that be possible to live without manufacturing anything, even the simple tools? Of course not. Even the early man manufactured simple tools for hunting, for cutting, and in order to make a home. So even if we want to live like an early man, still we need to manufacture some products. So we can say that it is impossible to live without manufacturing. When it is so important, so as a mechanical engineer who may be involved in manufacturing, we need to have a good understanding of manufacturing. Of course, if we are doing non-mechanical engineering courses, still it will be useful to us to make ourselves familiar with manufacturing to some extent, so that we will have a better understanding of the products that we are using, how it is manufactured, and what are the typical properties because of the manufacturing processes that are used in order to making it even useful for engineers doing non-mechanical engineering disciplines. Well, let's take a look at this product here. What we can see here is a modern tractor. Well, taking a look at the engine of the tractor, right here we can see that this is the engine, and in the engine, as we can see, there are hundreds of parts that are made to precise dimensions, and they are all assembled together and they work together in order to produce the required power for the tractor. Well, this tractor has to work in extremely hard conditions, and it has to last for a long time, and this won't be possible unless if all the parts, thousands of parts that are used in different parts of the tractor, are all precisely made to the predefined specifications, dimensions, and they all follow applied tolerances, and they all are subjected to certain manufacturing processes in order to function properly. And if there is one or a number of parts that are not made specifically to the predefined specifications, then they will make the tractor useless. So when it comes to manufacturing, all the parts are to follow the specified specifications, predefined specifications, in order to be able to be assembled in this large assembly. So it is very important to know how to process each of these parts in order to bring it to the desired shape, geometry, and it possesses the required properties and functionality to be used in a product like this. There are so many other examples around us, and this is just a typical one. Well, what is meant by manufacturing? The word manufacturing was first coined in 1567, and what it meant in those days was made by hand. Well, however, in modern manufacturing, it has got a broader definition that goes much beyond something that is made by hand. A modern definition or general definition that is given to this word is given in this slide, that is, manufacturing is the process of converting raw materials into useful products. Of course, we've got to make use of physical and chemical processes in order to make this possible. And what we can see here in this slide is one of the oldest manufacturing processes used by the mankind. What is it called? This process is called forging. Forging is the process of subjecting a metallic material to elevated temperature, heat it up in the furnace, and then subject it to hammering in order to bring it to the desired shape and geometry. And this is a really old process that has been in use for at least 10,000 years. In the old days, forging was the process, hammer forging was the process that was used in order to make so many tools, including the swords. And this process is still considered as an important manufacturing process. Of course, these days, the process has been automated, and instead of making use of human in order to hammer for the workpiece, we make use of modern machines, making it much more efficient. However, the process is still the same process, that is to heat the metallic material up to elevated temperature and subject to impact. Well, manufacturing is important. Why is this important? Why is manufacturing important? Well, we can say that manufacturing is important technologically, economically, and historically. Technologically, we can say that the application of science to provide society and its members with those things that are needed or desired. So manufacturing is technologically important because it is the application of science to make useful products, making our life easier and more comfortable and also safer. Manufacturing is important economically. What do we mean by this? Let's take a look at this table here. Well, as we can see in this table here, in the US, as an example of an industrial nation, in the US, manufacturing accounts for 15% of GNP. That is much greater than agriculture and minerals, accounting for only 5%, construction and utilities accounting for another 5%. Of course, far behind the service sector that accounts for 75% of the GNP. However, manufacturing, which accounts for 15%, is still a significant figure in the economy of the United States. More or less, it's the same for the developed countries like Australia. So, it is really important to the economy of any nation, the level of manufacturing. We can say that the higher the manufacturing level of the manufacturing technology of a nation, the higher the standard of living of that nation. And eventually, we can say that manufacturing is important historically. What is meant by this? Well, we can say that if we read history, we can realize that those nations that had a better manufacturing technology and those who were better at making things were more successful. Of course, when it comes to the wars, a nation which has got more advanced technology in manufacturing can make better weapons and they can succeed in the wars. And the ones who have got advanced manufacturing technology, of course, they can make more useful products and to sell them to the other nations and make more money out of it. Well, let's move on to the next slide. Again, we've got to know why manufacturing is important in this slide as well. If we take a look at figure A in this slide here, it's a representation of the raw material or the starting material that is subjected to manufacturing processes, and indeed machinery, different kinds of tools, power and labor are used in manufacturing processes in order to bring it to the desired shape and geometry in order to make the process part. And in doing this, of course, if we are required to remove some material from the raw material, we've got to remove some scrap and waste from the raw material in order to produce the process part. We will end up with something in the form of scrap and wasted material, and also the process part which will have a shape and geometry different from the starting raw material. This is the look of technical people or engineers to the manufacturing process. That is to receive the starting raw material, subject it to a manufacturing process and bring it to the desired shape and geometry that is now useful. An example to this could be, for example, to take or to receive a thin bar. That is a bar or a wire of metallic material, and then subjected to bending processes and eventually produce a coat hanger from it. When it was in the initial shape, that was just a straight bar, it was almost useless. But when the shape of it is changed after processing to a coat hanger, now it becomes a useful product. So this is the technical view to this process. We can also look at manufacturing as an economic process rather than a technical process. If we take a look at the one in B, this is a representation of manufacturing from an economic point of view. That is, we receive the initial raw material, we subject it to manufacturing processes in order to add value to the raw material, and eventually what is produced is the final product, and the price or the value of the final product will be greater than the raw material. So manufacturing process has added value to the starting raw material. Again, the example is the straight bar. When it is in the form of a straight bar, it has a certain value. After it is subjected to the manufacturing process and is converted to the form of a coat hanger, then its price or value will be greater than the initial price. So it has added value. Well, let's move on. There is a classification for different industries. In this slide here we can see that we can classify industries into three different industries. Those are primary industries, secondary industries, and tertiary industries. A primary industry is one that cultivates and exploits natural resources, such as agriculture or mining. A secondary industry takes the output of primary industries and converts them to consumer and capital goods. What are the examples for the secondary industry? Well, of course, manufacturing is the principal activity. Examples of secondary industries are textile and electronics. And eventually tertiary industries. A tertiary industry is in the service sector of the economy. Examples of tertiary industries include banking and education. And the image we have got here, down here, is the representation of a tertiary industry. Is this building familiar to you? Oh yes, you're right. This is the picture of ECU library. That is representation of a tertiary industry. Well, let's move on. Well, let's talk about production quantity. Well, quantity of products will have an impact on the technology that is used in a typical manufacturing organization or plant. Well, in this slide here we can see different types of products that are shown at the bottom of the slide. To the left we have different sizes and shapes of drill bits. At the bottom, in the center of the bottom, we have got a number of different types of machine tools. And to the left of the figures, we have got the image of a plant that is manufacturing aircrafts, large aircrafts. Well, as we can see, the shape, variety, and also size of these products are very different from one another. Well, depending on the production range and annual quantity, we can divide manufacturing plants or manufacturing volume into three different categories, and those include low production. In low production, the quantity of the parts produced are between 1 to 100 units per year. And then, according to this definition, which one of the products that are given at the bottom of the slide can be categorized among these? Yes, correct. The one to the bottom left, that is the aircraft. Often there are between 1 to 100 aircrafts of a kind that are produced in an aircraft manufacturing company. So this is grouped in the low production in terms of production volume or quantity. And the second category is medium production. In medium production, the typical quantity of the parts produced are between 100 to 10,000 units. And which one of the example products given here can be classified as the one that falls within this category? That is the one in the middle, of course. Machine tools. The number of machine tools of a kind that are produced in a year are often within this range. And then when it comes to the other product, that is the drill bits, the quantity of this type of products fall within the 10,000 to millions of products per year. And then this is regarded as high production. The manufacturing system, facilities, and the skill level of the people who are actually working in a company in order to make all these products are very different from one another, and to a large extent the skill level, the type of the machine tools, and the arrangement of the machine tools in a typical manufacturing company is a function of production range or production quantity. The other term that we need to make ourselves familiar with is production variety, or P. Well, production variety refers to the different product types or models that are produced in a manufacturing company or plant. Well, of course, again, this is a actually factor for determination of the skill level, the types of the machine tools, and also the arrangement of the machines in a manufacturing company. When the number of product types made in a company is really high, then it means that the production variety in this company is high or very high. And we can also classify production variety in terms of soft product variety or hard product variety. Soft product variety applies to the case when differences between products is small. That is, for example, a company is producing different models of the same product that are similar to one another. Like what? Like different types of vacuum cleaners. We are producing different products in a company. They are different from one another, and they have got some parts in common, and of course some parts that are different. And even those parts that are used in different types of product are different from one another, they are similar. So the same technology, the same type of the machine tools and skilled people are used in order to make these different types of products. However, in the case of hard product variety, products differ substantially, and there are few or even no parts that are in common. That is, we've got a company that is producing very different types of products, and maybe two products that are made in this company don't have even a single part in common. Well, this requires a high level of flexibility in the machine tools, in the production method, and in the skill level of the people who work for that company in order to make them. What is an example for hard product variety? Well, manufacturing of machining fixtures. Each fixture is used for production of a typical part that cannot be used for production of another part. Another example is the production of special machine tools. Special machine tools are the ones that are used in order to machine a typical part, and the same machine cannot be used in order to make another part. Another example is the manufacturing of, say, dyes and molds that are frequently used in manufacturing operations. Again, a dye or mold that is designed and produced for producing a typical part cannot be used for another part. We've got to scrap it and design and make another mold for production of another part. Okay, now let's take a look at this slide that is making a comparison, or indeed it's trying to establish a relationship between production variety P and production quantity Q. In the horizontal axis we have got production quantity right here, starting from low going to very high quantity, and in the vertical axis we have got production variety. Well, as we can see, manufacturing plants are specialized in a way that they can produce different types of parts and different quantity of parts in a way that the production variety and quantity lies somewhere within the shaded region right here. When, according to this figure, when production quantity is low within this region, then production variety could be high. Production variety is high in this region and production quantity is low. And as we move from left to right horizontally within this region, we reach to a region where production variety is medium and also production quantity is medium. And moving further to the right, we reach to a region where production quantity is high and at the same time production variety is low. Indeed, we can say that generally production quantity is inversely related to production variety. Yes, that's true. Production quantity is inversely related to production variety. A factory that produces a large variety of products, somewhere here, will produce a smaller quantity of each. Quantity is low. And then a company that produces a single product, so production variety is low, then it can produce a large quantity of that single product, like somewhere here. And it's not possible for a company to produce a large number of parts within this region and the variety is also high, which ends up in somewhere here, which is outside of the shaded area. That is not possible. And of course, somewhere here, when production variety is low and production quantity is also low, that's not feasible. So the company cannot make money out of this, or it cannot make a reasonable profit if they do it this way. So it can be concluded that manufacturing plants tend to specialize in the combination of Q and P within the shaded area. And this is properly representing the PQ relationship. This slide here. Well, let's move on to the next slide and let's talk about manufacturing capability. Manufacturing capability refers to the technical and physical limitations of a manufacturing firm and each of its plants. Well, a manufacturing company cannot do everything, that's for sure. Examples are given in this slide. A machine shop cannot roll steel because it doesn't have the facilities and the skill level to do that. And of course, a steel mill cannot build cars, again because of the same reason. And what I have highlighted in the middle of this slide right here, it is very important, that why I have put it on the yellow background, is that a manufacturing company must do certain things, and it must do those things well, really well. It's not good to say that I'm a mechanical engineer and I can do anything which is related to mechanical engineering. If I'm a good mechanical engineer, I must do certain things in mechanical engineering, and I must do those things really well, better than anyone else, as much as I can. Same applies to a company. A company, even if the company has the facilities, must not be doing everything. It must be doing only certain things. It must be producing only certain types of products. And in doing so, it must produce those products better than other competitors in order to be successful in marketing the products that are manufactured. Well, and at the bottom of the slide we can see 3 building blocks of modern manufacturing. And those are materials, processes, and systems. Well, materials is the first building block of modern manufacturing, and this is what was covered in Materials and Manufacturing 1 unit. And in Materials and Manufacturing 2 we are covering this block, that is processes. We talk about manufacturing processes. And if you do Advanced Materials and Manufacturing unit, some of you will be doing this unit, then you will be made familiar with manufacturing systems, and then all the 3 units together will make you familiar with modern manufacturing. Well, indeed, there are 3 categories of capability in the textbook. If you study the textbook, if you read the textbook, there are 3 categories of capability mentioned in the text, and those are technological process capability, physical size and weight, and also production capacity. And I have listed all those 3 right here in this slide. So, manufacturing capability has got 3 categories, as you can see in this slide here: technological processing capability, physical product limitations, and also product capacity. And what are they? They are all briefly described in this slide here. Technological process capability puts a limit on what a manufacturing company can do. The available set of manufacturing processes in the company, and that includes skill level of the people, engineers, technicians, and all the people who work in the company, on what this company can do. The technology level of this company is at the level of producing just very basic parts, very elementary parts, or it is very advanced in a way that they can produce the most advanced products that are ever needed. Of course, physical product limitations play a role in what a company can do. That is the size and weight limitations on the parts that can be produced. If I have got a small turning machine, there is a limit for the type of the for the range of the parts that I can produce, and I cannot machine larger parts or smaller parts than the say machine actually allows me to do that. And the quantity of the production, there is a capacity for the production in any manufacturing company, and this puts a limit on the maximum quantity that a plant can produce. If we want to produce more, actually the current capacity of the manufacturing plant doesn't allow this, and I will have to add more machine tools, more equipment in order to make that possible. So depending on the facilities that are available in the company, there is a limit for the production capacity. So as a whole, we can say that manufacturing capability is a function of these three criteria that are listed here. Well, now let's provide a brief introduction or review of manufacturing, of materials in manufacturing. Well, we have learned this in materials and manufacturing 1 unit, that there are 3 basic groups of engineering materials, and those are listed here. That includes metals, ceramics, and polymers. Well, we have already been made familiar with each of these types of materials to some extent, of course, and we know that these types of basic engineering materials have different chemistries. They are not similar mechanically and also physically. In terms of mechanical and physical properties, they are different from one another, and those differences affect the manufacturing processes that can be used in order to make products out of them. Indeed, there is a relationship between the properties of the materials and manufacturing processes that can be utilized in order to shape these materials. Indeed, the properties of the materials put a limit on the range of manufacturing operations that can be used in order to bring these materials to the desired shape and geometry. Well, this is a typical example here. Sometimes we can make use of each of these 3 basic engineering materials in order to make the same product. This is an interesting example here. As we can see, we can make use of metals, glasses or ceramics, and also polymers in order to make the same product. And in this example, this product is the beverage container. This may not apply to other products, but for some typical products, either of these engineering materials can be used for producing the same product. Well, and also we can add another group of materials to the 3 basic engineering materials, and these ones are composites. In composites, often we have got a mixture of at least two basic engineering materials that are mixed to one another in order to make a material. Why is this needed? Well, sometimes we are after a set of properties that do not exist in each of the basic engineering materials. For example, if we are after a material that is very strong and rigid, at the same time it has to have a low density, and it has to be of lightweight. Which one of the basic engineering materials is providing us with this set of properties? It has to be strong at the same time, and it has to be very rigid, but it has to be of low weight. Of course, none of the basic engineering materials will provide us with this set of properties. So in order to do that, we may be interested in mixing 2 different types of engineering materials. For example, ceramics are very strong and rigid. However, they are very dense and they have a high weight to volume ratio. At the same time, polymers are of low weight and low density, but they are not rigid and strong. And if we have a combination of the two, that is a combination of polymers and ceramics, then we may end up with a ceramic and polymer composite. That is, we will be dealing with a material that is having some properties of the polymers, that is of low weight. At the same time, it is strong because we've got ceramics in it. So we may end up in a material which possesses a combination of the properties of the two participating materials in it. It may be also possible to have a mixture of the composite material which includes more than two types of engineering materials in it. Well, here we can see a classification of engineering materials. As we can see, engineering materials can be divided into three basic engineering materials plus one non-basic engineering material. Of course, in the case of the first three, we end up with a homogeneous material, but in the case of composites, we may end up in a non-homogeneous type of material. Well, we can further divide metallic materials into ferrous and non-ferrous materials. Ceramics can be further divided into crystalline ceramics and glasses, and also polymers can be further divided or subdivided into thermoplastics, thermosets, and also elastomers. And composite materials can be divided into three different classes, as we can see down here. Of course, we can further divide composites into a larger number of composite materials. However, we are not going to go into depths of different types of composites in this unit. We are just reviewing different types of materials briefly in this unit. When we do advanced materials and manufacturing unit, we will be made familiar with a broader classification of composites. Okay, as mentioned, metallic materials can be divided into two basic groups, and those are ferrous metals that are based on iron, Fe, and this comprises about 75%. It is a big number. 75% of metal tonnage goes to the ferrous metals, leaving only 25% for the rest of materials that are non-ferrous metals. It doesn't mean that the non-ferrous metals are not of importance. They are important, however, they are used for certain applications. Well, when we talk about ferrous materials, it should be noticed that we can divide ferrous metals into steels and cast irons depending on the carbon content. Each of these two are indeed products of iron and carbon as the main components, and in steels the carbon content of iron is between 0.022 to 2.14%. That's the carbon content of the product. There could be some other alloys in it, but the amount of the other elements will only change alter the resultant properties. These are the basic elements that should be present in steels. Iron and also carbon are the main elements in steels, and the range of the carbon content is this much. Well, in the textbook, slightly different figures are given, but to be consistent with what we will see later in Advanced Materials and Manufacturing unit, we stick to what is given up here that is more accurate. And in the case of cast irons, the carbon content is more than steels. That is, if the carbon content exceeds the maximum limit of carbon in steels, that is 2.14%, going all the way to 6.67% carbon content. If the carbon content is within this range, then the product is called cast iron and it's not considered as steel anymore. And again, in the textbook, in the present textbook, the carbon content is referred to as 2% to 4%. That is the range of most common types of cast irons. It's not incorrect. It is referring to the most common carbon content in cast irons, and the same applies to the definition that was given previously. And the maximum range of cast iron, maximum range of carbon content in steels that is given in the textbook is 2.14, but in most textbooks it is mentioned as 2.14. There are some differences, but anyway, the actual range that is more reliable is this one. Well, and we've got also non-ferrous metals such as aluminium and its alloys, copper, magnesium, nickel, and so many other ones, silver, titanium, gold, and so many other ones have got certain applications because of possessing different types of properties. Indeed, ferrous metals are susceptible to corrosion and they are dense and heavy. However, non-ferrous metals are not susceptible to corrosion, and in many cases their density and weight is less than that of ferrous metals. And because of this, for some certain application, we've got to go for non-ferrous metals and alloys rather than the ferrous metals and alloys. And in the case of ceramics, that are compounds containing metallic or semi-metallic and non-metallic elements, typical non-metallic elements that are present in ceramics are, say, oxygen, nitrogen, and carbon that are frequently present in the environment. They are not expensive. And because of this, often ceramic products are not expensive as well. Anyway, generally we can divide them into two broad categories, and those are crystalline ceramics and glasses. In the case of crystalline ceramics, atoms of the material are positioned in the crystalline structure in an orderly manner. That is, they are sitting in the right positions in the crystalline structure, providing the whole material with a crystalline structure, with an ordered crystalline structure. And this results in acquiring a material that has a high density and is extremely strong and rigid. In the case of glasses that are mostly based on silica, that is the silica sand we can find in the beaches, what we see, that the silica sand that we can see in the beach is silica sand, SiO2. That's inexpensive and that is frequently available. Glasses are made of silica sand, and the difference between the structure of glasses and crystalline ceramic is the crystalline structure. Indeed, crystalline ceramics have got a crystalline structure, as I mentioned before, but in the case of glasses, a crystalline structure is missing and atoms are positioned randomly in the structure, and there is a lack of an order in the placement of the atoms in the structure. They are solidified wherever they are because the process of cooling down the material to the room temperature is extremely high, and there is no time for the atoms to sit in the right position in the structure. So they are frozen in a way that there is no time for the atoms to sit in the right place in the structure, and there is a lack of order in the structure. So glasses haven't got a crystalline structure, and they are referred to as amorphous materials, and this provides them with the possibility of having a lower density compared to crystalline ceramics, and because of this there are some void spaces in between. The density is lower, and this also contributes to the transparency of glasses. Well, let's talk about polymers. We can divide polymers into three main groups as listed here. Those are thermoplastics, thermosetting polymers, and also elastomers. Indeed, when we talk about polymers, we are talking about long molecules that are referred to as macromolecules, that are also referred to the word polymer by itself means many mers, and each mer is a repeat unit that is successively repeated along the length of the molecule. Well, as I said, we can divide polymers into three categories. Those are listed here, that are thermoplastic polymers. Thermoplastics can be recycled. They can be subjected to multiple heating and cooling cycles, and the structure of the molecules will not change, so they can be used again and again and again. There is no limit. The second category is thermosetting polymers, where molecules are cured when they are subjected to heating. So we can only make use of this type of materials once, and when we do this, a network structure is formed. That is, long molecules are bonded to one another in the form of a network. So a rigid product is produced that is very strong, very rigid. However, the problem is that they cannot be recycled and reused. Once they are made in order to make a part, that's forever, and they cannot be reheated and recycled. Same applies to elastomers. However, the network is not dense. That applies to thermosetting polymers. In elastomers, we've got also a network. However, the number of links that are formed between adjacent molecules is significantly less than that of thermosetting molecules. So because of this, if we are using elastomers, we can extend them to a length that is up to 10 times of the original length. Once you release the load, they return to the original shape, and this is a property that can only be found in elastomers. However, they cannot be recycled. The reason is the same reason that we had for thermosetting polymers. And when it comes to composites, as mentioned before, these are materials that consist of two or more phases. And in this type of materials, we are dealing with non-homogeneous materials. What is meant by this? It means that a material is made of different phases. There is often a matrix phase, and there is a stronger phase that is embedded inside of the matrix phase. For example, we've got a matrix of polymer that is of lightweight, and inside of it there are some particles of a stronger phase that could be particles of ceramic or metallic material that is stronger than polymer, and those are embedded inside of the material in the form of particles that are round in shape, or fibers that have got a long length to diameter ratio. And once this material, that is a composite material made of polymer and an embedded phase, are subjected to forces, those strong particles that are inside of the polymer increase the strength of the material, so it can be subjected to higher amount of force and stress before it fails. Well, of course, properties of composites depend on the physical shape of the components that are embedded inside of the matrix phase, and also the distribution of the those particles or fibers that are inside of the matrix phase will contribute to the resulting properties of the composite materials. Well, in this slide here we can see a description or classification of different manufacturing processes. Well, generally we can divide manufacturing processes into two broad categories, and those are processing operations, including shaping processes, property enhancing or property enhancement, and surface processing. Well, we know that processing operations generally change the shape, property, and also appearance of the material. And in the case of shaping processes, we can further divide shaping processes into four categories as shown up here. Those are solidification processes such as casting, particulate processing, or powder metallurgy, where a powder of the material is used in order to make the product. Deformation processes that are used in order to change the shape and geometry of the material, such as rolling and forging operations, and material removal processes that include machining processes. Property enhancing processes that include heat treatment processes will not be covered in this unit, that will be covered in advanced materials and manufacturing unit. And then surface processing methods that include cleaning and surface treatment, coating and depositioning processes will not be discussed in this unit. Well, and when it comes to assembly operations, if we are dealing with those type of products that consist more than one part, then we've got to make use of assembly operations, and sometimes we've got to join these parts together in order to make a single product. To do that, we've got to make use of either permanent joining processes, including welding, brazing, and soldering operations listed down here. Welding, brazing, and soldering, and also sometimes we make use of adhesive bonding in order to join material parts to one another. And also we can make use of mechanical fastening operations that include use of threaded fastening and also permanent fastening operations in order to make that happen. What is an example for threaded riveting is threaded fastening and permanent fastening? Well, that's right. An example for threaded fastening would be use of bolts and nuts, and an example for permanent fastening would be what? Yes. An example for permanent fastening would be use of rivets or riveting. Correct. Well, in this slide here we can see a simple representation of solidification of a typical and very common solidification process, that is metal casting. In this process, what we do, the most common type of casting process is to make use of sand in order to make the mold. And as we can see here, sand is packed in a way that a cavity is accommodated in it by making use of a model, and the cavity is filled in with molten material. When it solidifies, it will have the desired shape and geometry. We will actually study casting in one of the lectures in this unit, and this process is commonly used in making those parts that are bulky often, and also they have intricate shapes, like this figure here that you can see is the body, is the engine block, and as you can see it has got very intricate shape. And to make to produce this shape by making use of a process such as machining would be very expensive and very hard. However, we can make intricate shapes by making use of casting process, as we can see in this figure here. Well, in this slide here we can see a presentation of particulate processing or powder metallurgy, where, as mentioned before, starting materials are powders of metallic materials and sometimes ceramics, and the powder of the material is compressed, as you can see in this mechanism here, and it is pressed from both of the sides so that a very dense volume of the material is resulted, and it is highly packed. If we take a look at the individual atoms here, we can see that this is the initial formation and there are some void spaces in between, and when it is subjected to pressure they are densely packed to one another, and to some extent, as you can see, there is very small void spaces left in between, and it is highly packed and it's very dense. When it is highly dense, it will be subjected to elevated temperature, which will improve bonding, and after some time, once the sintering is completed, if we take it out, it will result in a part which will have the shape and geometry of the space in the mechanism, just like that one. And this process provides us with achieving very actually accurate shapes and with high precision, and those parts are very expensive and are used for certain applications. What is a typical application for those parts that are produced in this method? Well, tiny parts that are precisely made to the given size and geometry. A typical application is the cutting tool tip, the inserts that are used in carbide tools. The cutting tip is produced by making use of this method, and it is also subjected to a number of layers of different types of coatings in order to increase its resistance to wear. So once you go to the lab, if you take a close look at the tip of the cutting tool, you will see some inserts that are used, and those have different shapes and geometries, and they are all produced by making use of this process. Well, in this slide here we can see two different deformation processes that are in this process. By making use of force, we change the shape and geometry of the raw material. In here we can see the forging process. In the forging process we make use of a die, and the material is heated up and it is subjected to impact or pressure in a way that the shape of the raw material will be converted into the shape of the cavity designed in the die, just like that one. So initial part will have a different shape when it is subjected to impact or pressure. It will take the shape of the cavity in the die. And in this process here, we've got a sheet metal which is actually rolled between two opposing rolls, and what happens is that the thickness of the sheet metal will be reduced to the distance between the two rolls, and also it may have a different shape. If you take a look at the profile of the shape, it may also have different shape. Sometimes it is flat, sometimes it will have a non-flat shape. We can change the shape and also size of the rolled steel or any metallic material to the desired shape and geometry. We will discuss both of these methods in one of the lectures in this unit. And in this slide here we can see two other deformation processes. Those include drawing. In the drawing process there is a die here and the material is pulled out of the die opening, and when this happens the shape and geometry of the die opening will be left on the material. We can do it the other way, that is to press the material and to push it out of the cavity. Again, the shape and geometry of the die opening will be left on the product that is extruded through it. So this process is referred to as extrusion. Both of these methods can be done in hot and cold conditions. That is, the material that is to be drawn or extruded could be at room temperature before it is subjected to this process, or it could be at elevated temperature. Of course, if temperature is elevated, there is a need for lower force in order to make that happen. And down here we can see a number of examples of the parts that are produced by the extrusion method, and these are typically used in industry. Well, and in this slide here we can see three different processes that are commonly performed in metal removal processes or machining processes. And in these processes a cutting tool is used in order to remove the unwanted portions of the material in order to bring it to the desired shape and geometry. In A, we can see a turning operation when a round material rotates and the cutting tool is not rotating, however, it moves along the legs of the material in order to take the cut. So this process is used in order to produce rotational parts. In drilling, a round rotating cutting tool is used in order to make a round hole onto the workpiece that is stationary. We are all familiar with this process. And in the milling operation, again we make use of a round rotating cutting tool similar to drilling. However, the difference is that in this case the workpiece also moves, as you can see, along the feed direction in order to make it possible for the cutting tool to take the cut from it. In drilling and milling operations, there are multiple cutting edges on the cutting tool. However, in turning there is only a single cutting edge that is taking the cut. We will study all these processes in this unit in details, and we will do a number of problems on each of these processes. Well, waste in shaping processes is very important. Indeed, when we are making use of materials, we are paying a lot of money in order to buy the raw material to be used in order to produce different parts out of it. And when we are making use of the raw materials, indeed we are using our resources that are limited, and they are not unlimited. So an engineer should be very careful in what process he or she is using in order to bring the part to the desired shape and geometry. And always a process that has a lower waste is preferred as long as possible. In material removal processes, we are all wasting the material. Why is this? Take a look at this figure up here. This is the representation of a face milling operation. And we are actually making use of the machine. We are paying for the cutting tool. We are paying for the running cost of the machine. and we are also paying for the raw material. And then what is this process doing? It is converting a portion of the raw material. We have paid for it, and we are making use of this process in order to convert some portion of the material, of the useful material, to the waste, that is the swarf. And this is useless. And again, we've got to pay someone in order to take it away, to remove it. And this could be a hazard to the environment as well. So it's always preferred to make use of the processes that do not waste the material, rather than the ones that waste the material. However, having said that, material removal processes or machining processes that are wasteful are the most common manufacturing processes used in the industry. Reason, there are certain reasons for doing machining operations. One of them is cost. Compared to some other processes, machining processes are not as costly as some other processes. Not just that. There are some certain properties that can be achieved when a part is machined. Those include precision and accuracy, high surface finish, and yes, achieving tight tolerances. These are the reasons why we cannot avoid making use of material removal processes. However, it's a good idea to limit them as much as we can. And there are some processes such as casting, molding, and particulate processing. These are the operations that do not waste the material. All the initial material or the raw material that is used is converted into the desired product. So these processes are not wasting the material. But however, sometimes we cannot make use of these processes, and we've got to use the machining process in order to bring the part to completion. If this is the case, it's a good idea to limit the amount of machining processes to minimum. For example, we can make use of the casting process in order to make the part, and only certain surfaces and portions of that part that is produced by casting should be subjected to limited machining so that the waste of material will be minimized. Let's take a look at this figure here. We have got the same part that is produced by 5 different processes. Those include casting in A, B, forging or offsetting, C, extrusion, D, machining, and E, that is joining. And as we can see, it's only in D, or machining, that we are wasting the material. As you can see, this portion of the material will be removed and it will be converted to swarf that is useless. In the other ones, we are not wasting the material. So this is the least desirable manufacturing method, and we've got to avoid it as long as we can. Okay, let's move on. And here we can see actually 2 different possibilities when it comes to eliminating the waste of the material in the shaping process. There are 2 terms that are introduced in this slide. Those are net shape processes, that is applied when most of the starting material is used and it doesn't require any subsequent machining operations, so we are not wasting the material at all, and all of the material that is used that was present initially has been converted into the final shape, and there is no wastage of the material. And an example for this type of processing is investment casting. As you can see here, we have got a number of parts that are produced by investment casting, and in this process we can produce intricate parts with intricate shapes, and the level of accuracy and precision of the parts are so high that often they do not require even minimum amount of machining operation, and you can achieve the final shape and geometry with no machining. And this process is referred to as one of the net shape processes. There is another process similar to casting when we can limit the amount of machining to minimum. For example, for this part, as we can see here, we can make the model in a way that we produce something that is close to the final shape, but it requires minimum machining, that is to take a surface off from here in order to bring it to the desired size and accuracy and surface finish and remove the top part. These are the risers, and this is the sprue and the runner that actually is used in order to produce this part in the casting process, and these parts will be cut away. All these extra sections will be cut away, and these go back to the furnace again, will be remelted and will be reused in order to make another part. So even if there is some machining in this part, the material that is machined and it is cut from this will not be wasted, will be reused again. So both casting and investment casting processes, gravity casting and investment casting processes, are the ones that do not waste the material. Well, and let's have a brief review of production systems. In this slide here, we can see the overview of a production system. As we can see in this figure, we've got engineering materials that enter the system. They are subject to manufacturing and assembly operations, and eventually a finished product is produced. In doing so, in the manufacturing processes, we've got to make use of manufacturing systems. What is meant by manufacturing system? How the machine tools are arranged in the organization. What is the layout? What layout is used? What is the arrangement of the machines? What is the location of each of the machines in the manufacturing plant? And what is the system of transferring parts from one machine to another one? There are different manufacturing systems that will be studied in the Advanced Materials and Manufacturing unit. We are not going to go into details of this. And also the quality control systems are the ones to be used in order to see either whether the parts that we are producing are made to the pre-specified dimensions and shapes. Are they acceptable, or if they are not? And also the quality control system will take the input from the from the production line in order to correct or to modify manufacturing system and manufacturing support systems that are used in order to support manufacturing systems. Some typical applications in manufacturing support systems include production planning and control. Let's take a look at the next slide here, which is actually showing, again, describing different types of production processes. As discussed before, we have got production systems that are divided into production facilities as well as manufacturing support systems. Well, production facilities, according to the quantity of the production, can be subdivided into low production or job shop, medium production, and high production. With the medium production, we can further divide it into batch production and cellular manufacturing. And cellular manufacturing, again, will be discussed in Advanced Materials and Manufacturing, will not be discussed in this unit. And batch production is where groups, lots, or batches of materials or parts are processed together through the manufacturing operations. In batch production, all units in the batch are processed at the given station before the group proceeds to the next station. In medium or low quantity production, the same machines are used to produce many types of products. Whenever a machine from one product, whenever machine switches from one product to another, a changeover is required. The changeover requires the machine setup to be torn down and set up for the new product. In the case of batch production, it allows the changeover time to be distributed across a large number of parts, and hence it will reduce the average operation time per piece. It will reduce the average operation time per piece because we are doing batch production. We set up the machine only once for a batch of parts, for a number of parts that is, for example, 10, 50, 100 or more, depending on the number of parts in a batch. We set the machine up, it may take 1 hour, 1.5 hours or whatever, and then we produce a large number of parts. So the setup time will be divided, for each part will be the total setup time divided by the number of parts, which is not the case in low production. And the story of cellular manufacturing is totally different. We divide all the machine tools in the manufacturing firm into a number of machine cells. Each of the machine cells is specialized in producing one or a group of similar parts. And as I said before, this will not be discussed further in this unit. In the case of high production, or mass production, a large number of parts, of course with low variety, are produced. In order to achieve this, we've got to make use of special machines, special tooling, jigs, fixtures, and whatever, and also different types of layout, two different types of layouts that include process layout and cellular layout will be used in order to make this happen. And sometimes we make use of flow line production in order to produce a large number of parts. In flow line production, product is complex, and we are required, in order to arrange the machines in a way that these complex parts can be machined in a way that production flow is continuous. Well, let's take a look at different layouts, as we can see in this slide here. Well, we have got on the top left, we have got an aircraft that is produced. As you can see, this is a large product, and for producing a large product like an aircraft, we've got to make use of fixed position layout. What does this mean? It means that the position of the part is fixed. Part of product is fixed and it doesn't change, because the product is really big. It's not easy to make it move from one working station to another. Rather, we make the equipment or the machine tools move around it. So in fixed position layout, the product is in a fixed position, and it's the equipment that make them move. They come close to the product while they are processing the product, and once the task is done, they move away and other piece of equipment is brought next to the product. In the process layout, all the machine tools that are used in the manufacturing plant are positioned or placed according to the type of the machine. For example, we have got all the lathes sitting here in this department, all the milling machines in another department, grinding machines, drilling machines, assembly machines, whatever we have got. Depending on the type of the machines, they are sitting in a different department. Indeed, we can say that a process layout is the one where the machinery in a plant is arranged based on the type of the process it performs. And in this case, to produce a product, the part must visit the departments in the order of the operations that must be performed. So the part moves from this department to the next department, then to the other department. It goes all the way and visits all the required departments in order to be completed. So Once its processing is completed, it leaves the manufacturing plant once it visits all the required machines. It doesn't mean that a part has to visit all the departments. It meets all the departments that are needed to work on it. It may be all the departments, could be a number of them. This often includes large travel distances within the plant. A process layout is often used when the product variety is large and the operation sequences of products are dissimilar, of course. So this is desirable when production variety is high, and at different times a new part may be introduced to the production plant. And let's take a look at this one down here. We've got the product layout. A product layout is one where machinery is arranged based on the general flow of the product that will be produced. As we can see, we've got a number of workstations along the line, and there could be a transfer line which transfers the part from the first workstation to the next, and it goes all the way until it is completed. And often a conveyor system is used in order to automate the function of transferring parts from one workstation to another. In this case, travel distance is reduced because products will generally flow to the next machine in the sequence. And this type of layout, that is product layout, works well when all products tend to allow the same sequence of production, because the sequence doesn't change and it is always fixed. And in cellular manufacturing or cellular layout, this one, a number of machine cells are produced. As we can see here, we can see two small machine cells in this manufacturing plant. And the machines are arranged into small cells, and each of the cells is specializing in production of one or a family of similar parts. So those machines that are required in order to make that given part or that family of parts, they are placed in a machine cell in the right order, and this will increase the productivity of the plant significantly. Well, now let's take a look at the cost breakdown. Here in this slide we can see a typical breakdown of the cost for a manufacturing product. As you can see, if this is representation of all the manufacturing costs, we can see that 40% of manufacturing of the production cost goes to the manufacturing cost, direct manufacturing cost I mean, and of this 40%, 12% goes to direct labor and 12% goes to indirect labor. What is meant by this? It means the cost that we've got to pay in order to make the labor work other than his wages. This is representative of his wages, and this is the overhead cost or indirect labor cost. That includes superannuation, paying for the superannuation of the worker, paying for the services that we are offering to the employer, and whatever. These are indirect costs of the labor. We are not paying this to the labor himself. However, these are to be paid in order to make him work for us. 26% of this manufacturing cost goes to the plant and machinery, such as depreciation, electricity, and maintenance, and those costs that we've got to pay in order to make the machine work. And 50% of the manufacturing cost belongs to the cost of the raw material and parts that we need, standard parts that we may need to buy in order to continue with our production task. And of the remaining sections or percentages of the production cost, 15% go to manufacturing activities such as preparing engineering drawings and production planning and that sort of things. 5% will go to research and development of the parts that we will manufacture in the future or improvement of the existing part. 25% goes to administration, sales and marketing, and 15% of this is profit. This is a typical representation of the breakdown of the cost in manufacturing environments.